Let's review sections 3.1 through 3.3 in Unit 3. This goes pretty quickly, so if I go too fast for you, you can always stop and pause and re-look at the information. If you're using your textbook, this is Chapter 10, Intermolecular Forces and Properties of Solids, Liquids, and Gases. What we're really trying to do is to be able to look at a chemical formula and determine, based on its structure, whether it's ionic, whether it's metallic, which of course alloys are a form of metallic bonding, whether or not you have the ability to hydrogen bond, whether or not you are a non-polar or polar compound, and based on that, you're able to determine some physical properties. So remember, all of the physical properties depend on those intermolecular forces, and those forces depend on your structure, which depends on your intramolecular. So in your previous chapters, you were looking at your covalent bonding, your ionic bonding, that now will affect the intermolecular forces based on the structure and pretty much based on the polarity of that molecule. We're really looking at the simplicity of whether a molecule is polar or not. So your stronger forces exist within your molecule, between your atoms or ions, your ionic and covalent. These are strong forces. Your weaker forces are between your molecules. These are your intermolecular forces, your hydrogen bonding, dipole-dipole. These are what give your substance their properties, these weaker interparticle forces. So we've talked about ionic solids numerous times, but just to reinforce, your ionic solid has a structural unit of an ion. The bonding is ionic. You have hard, high melting point substances. They are insulators in their solid form. They are conductors in solution. So any ionic compound that's soluble will be an electrolyte or a conductor when dissolved in solution, but not as a solid. Your ionic bonding and your ion forces can be varied and compared based on Coulomb's law. You're looking at the charges and the radius, the distance between those ions, to give you a comparison of ionic bonding strength. We know they're brittle because the strong repulsive forces will force the crystal apart. Your ionic bonding is pretty simple compared to your molecular compounds. Your molecular compounds have far more choices of the type of intermolecular forces. So let's look first at one of the strongest, which would be your dipole-dipole attraction. These are your polar molecules, so dipole-dipole means two poles, so these are polar molecules. They have a permanent dipole, a permanent separation of charge, where you have the positive end of one molecule attracted permanently to the negative end of another. It's not as strong as ionic bonding because notice these are only partial charges, but they are a permanent attraction, and the dipoles will hold these molecules pretty close together. So your dipole forces, if you're looking at comparing strength, ionic, for the most part, is going to be stronger than your dipole-dipole forces due to those partial charges instead of your complete and total charge. So you've got these partial charges. Within your dipole-dipole, you have a subset of bonding called hydrogen bonding. And the term bonding is a little misleading. This is an intermolecular force. This is not the bond that takes place between hydrogen and an electronegative element. Okay, this bond is a covalent bond. That's not the hydrogen bond. We're talking about an intermolecular force that's basically dipole-dipole, positive end of one, negative end of the other, but because of the high electronegativity of these fluorine, oxygen, or nitrogen atoms, you have a very strong attraction for the positive hydrogen. And because the hydrogen is so small, the hydrogen on one molecule can get very close to the fluorine or oxygen or nitrogen on the other. And it's pulled very closely because of this high electronegativity. So it's still just a dipole, just extremely strong because of the small hydrogen and the high electronegativity. So some of the more common hydrogen bonded compounds are water and HF and NH3. So you often will be asked to draw a hydrogen bond or to circle where that hydrogen bonding exists. So when you're doing that, you're looking at this intermolecular force, not those bonds. Many students will confuse those bondings, and you need to have your hydrogen on one molecule covalently bonded to NO or F. So this meets that criteria. And then the hydrogen on that molecule is attracted to the NO or F on the other molecule. That is the intermolecular hydrogen bond. The boiling points for molecules that hydrogen bond are much higher than other elements in that same group. If you were going down oxygen's group, oxygen, sulfur, selenium, tellurium, and bonding it with hydrogen, you would see that even though you have much larger molecules here, okay, so as a normal trend, as the molar mass goes up, boiling point goes up. But notice that water's boiling point is much, much higher than the others, and this is again based on that hydrogen bonding. The ability to attract molecules of the same type and other molecules that can hydrogen bond. That same trend is seen in all of the groups. If you go down the halogen group of HF, HCl, HBr, HI, you see the normal increasing trend as molar mass goes up, but a huge change even with the smaller mass of HF. After you have those permanent dipoles and ionic bonding, then you have attractive forces where you have a nonpolar molecule. So nonpolar molecules also can attract each other. Otherwise, you couldn't have solid, liquid, or gas states of matter. So when you have, and nonpolar molecules have only London dispersion forces, but all molecules have London dispersion forces. At any given time, the electrons in a molecule become unevenly distributed. They create a temporary polarity or an instantaneous dipole. That means you have a positive negative end that instantly occurs within the molecule. This induces a polarity in the molecule next to it. So now you have a temporary positive and negative force of attraction, and they interact. But these are not permanent dipoles. So when you're looking at your London dispersion forces, let's look at the simple molecule hydrogen. You have a disruption in the electron cloud that leads to a positive negative end. So you have more of your electrons for some reason ending up over here. This induces a polarity in the molecule next to it, and a short attractive force exists, but they disappear very quickly. They are short and they are not long-lived. So all substances have these LDF forces, but for nonpolar, they're the only forces. And the factors that affect them are the size of the molecule. So if you have a larger molecule, you have more electrons and more chances for this polarizability, meaning creation of a polar molecule. And you can have, in a large molecule, a lot of these London dispersion forces, and they can become quite significant. While we often think they're much, much weaker than other IMFs, they can actually, in a large molecule, be stronger than even hydrogen bonding. So they are weak forces, but they can become quite significant. And one of the things they're going to try to trip you up on is that you think, well, if it's London dispersion, it's weaker, lower boiling point, and you'll see that's not always the case. They are weak and short-lived within each individual attractive force, but the more of them you have, they become quite significant. And if you cool down your substance, you can get them to last longer as well. So in general, you have ionic bonding, that's pretty straightforward, metal, nonmetal ions. Polar molecules can be dipole-dipole or hydrogen bonding. And then if you're non-polar, you're going to be London dispersion forces. The strengths of these are pretty generalized here, but there's quite a bit of overlap. As we said, London dispersion forces can be stronger than dipole-dipole, and they can even be stronger than hydrogen bonding. And dipole-dipole can be stronger than hydrogen bonding if there are a significant number of London dispersion forces. So you always want to look at those London dispersion forces as they are present in all molecules.